Okay, so in this lecture we'll cover this concept of nuclear stability and then also nuclear decay series. So why is a nucleus stable at all? Doesn't seem like it should be stable because compared to an electron cloud, a nucleus is about 100,000 times smaller. So how is it that you can pack so many protons that are positively charged in such a small space? Because obviously positives are going to be repelled by other positives. And so that is true, but once they get into really small space, really close to each other, then there's actually an attraction between between protons. And so that's due to what's called a nuclear binding force. And so we can calculate this nuclear binding energy or nuclear binding force. So if we take a helium atom as an example, so helium has 2 protons, 2 electrons. Helium-4 has 2 electrons, 2 protons, 2 neutrons. So 2 electrons, so the mass of an electron is 0.000549 atomic mass units per electron. So there's 2 electrons, so 0.00110 atomic mass units. Proton has a mass 1.00728 atomic mass units per proton, and there's 2 protons. So 2.01456 AMU, and a neutron is slightly heavier than a proton. So 1.00867 AMU per neutron, and there's 2 neutrons. So if we add up the mass of a helium, it should weigh 4.03300 AMU, right, but it doesn't. So mass of a helium atom should be 4.03300 AMU, but it's but it's actually 4.00260 AMU. So it's a mass difference of 0.03040 AMU. So it's what's called the mass defect, right? It's how much less it weighs compared to what it should weigh. So where is this mass at? Because 2 protons, 2 neutrons, 2 electrons should weigh 4.033 AMU, but it doesn't if it's in a helium atom. So where's that mass at? Well, according to Einstein, right, mass can be converted to energy, and so E equals mc squared. So if we do this calculation, so E equals change in mass times speed of light squared. So 0.030, so AMU, you could convert that to grams per mole. So 0.0304 grams, mass defect. And if we convert that to kilograms, so that's the change in mass times the speed of light squared. So 2.998 times 10 to the 8 meters per second, and square that. Then you get 2.732 times 10 to the 12. That would be a kilogram meters squared per second squared. 1 kilogram meter squared per second squared is the same thing as 1 joule. So for 1 mole of helium atoms, then has nuclear binding force of 2.732 times 10 to the 12 joules. So that's the energy that's holding this entire nucleus together. Okay, so similar to electrons, so of course if you know from Gen Chem 1, electrons exist in shells about the nucleus, so there's certain numbers of electrons that are very stable, like in the noble gases. and electrons exist in shells, right? The first shell can have 2 electrons, the second shell can have 8 electrons, the third can have 18, and then 32 and 50 electrons and so forth. So electrons exist in the shell. The same is true for nuclei. Protons and neutrons exist in shells within the nucleus. So there's certain numbers of protons and neutrons that are stable. It's what's called the magic numbers. So for protons, magic numbers are 2 protons or 8 protons, 20, 28, 50, 82, and it's predicted that 114 would be stable as well. But there are no elements known with 114 protons at this point. It's just theoretically predicted to be stable. And for neutrons, 2, 8, 20, 28, 50, 82, and 126 neutrons in an atom is the magic numbers that seem to be extra stable. Okay, so for the different nuclei, if we look at the protons and neutrons, so if they're both even numbers of both in an atom, then there are 157 known nuclei that are stable. If you have an even number of protons and an odd number of neutrons, then there's only 52 nuclei that are known to be stable. An odd number of protons and an even number of neutrons, 50 nuclei that are known to be stable. And if you have an odd number of protons and neutrons, there's only 5 that are known to be stable. So obviously it's nucleus is more stable if both the number of protons and neutrons is even, or if one is even as one is odd. If they're both odd, not likely to give a stable nucleus. So, without question, nuclear stability is not as well understood as electron clouds are. And it's harder to predict just looking at something, whether it's going to be stable or not. So one thing that is done is to create a little graphic like this, where if you plot the number of neutrons versus the number of protons, so this will be a 1-to-1 ratio. And so this is looking at the stability of different nuclei, and basically what's found is that at low numbers of protons and neutrons, there's about a 1-to-1 ratio of protons and neutrons that's stable. But as the number of protons grows, then there's more neutrons than protons in the nucleus to help stabilize the nucleus. So as the number of protons increase, then there's more neutrons needed in the nucleus to stabilize it. And that's maybe not surprising, because as you get a lot of protons in there, then the repulsion starts to become more and more important. And at some point, if too many protons are in the nucleus, then the nucleus just becomes unstable at all. And so that happens at 83 protons. So there are no stable nuclei if the number of protons is greater than 83. So every single element, every single atom that has more than 83 protons in its nucleus is radioactive, and it's going to decay over time to something that's more stable. Okay, so again, if we look at the ratio of neutrons to protons, so if that ratio is too large, so that means if you're in this region, so too many neutrons, not enough protons, then the nucleus becomes unstable. And so what you need then is you need more protons and less neutrons in order to decrease that ratio. So a neutron can be converted to a proton and an electron. So those type of nuclei tend to undergo beta decay, right? They give off, convert a neutron to a proton and give off an electron. If the neutron to proton ratio is too small, so if you're in this region, so if you have too many protons, not enough neutrons, then you need more neutrons and less protons, so then this nuclear reaction can happen. So a proton can be converted into a neutron, so that would increase the ratio. And so in this case, these type of nuclei will tend to undergo positron emission or electron capture, which will both change that ratio to increase the ratio. And then again, if Z is too large, if it's greater than 83, then the nucleus is not stable, and that generally leads to alpha emission. So you can lose 4 protons or 2 protons, 2 neutrons at a time, and they emit an alpha particle, or it can undergo spontaneous fission and break apart into smaller nuclei. So if we take an example, so carbon-11, so what type of nuclear decay should this undergo? So it's got 5 neutrons and it's got 6 protons. So that ratio is less than 1. So that means you're in this region, right? So that should undergo positron emission, which is what happens in this case. So carbon-11 nucleus is converted into a boron-11 nucleus plus a positron emission. And so now if we look at the ratio in boron-11, so it's got 6 neutrons to 5 protons. So it's closer to that ratio of 1:1 or slightly greater than a 1:1 ratio. Okay, so nuclei that are not stable and large nuclei, something like a uranium-238. So 92 protons, so greater than 83, so it's not a stable nucleus, so it's going to undergo radioactive decay. And so what some nuclei do is undergo a sequence of nuclear decays. So one radioactive element is converted to another radioactive element, in this case 234, thorium-234. Well, that's still radioactive, so this undergoes another nuclear decay. In this case, you make protactinium-234, and that's still radioactive, so that undergoes another nuclear decay, in this case to uranium-234. Right, so the first step, we had an alpha particle emission, and then a beta emission, and then another beta emission, and then uranium-234 will undergo radioactive decay to thorium-230 by an alpha particle emission, and so forth. The nucleus just keeps decaying until ultimately you get to something that's stable. In this case, the radioactive decay series ends at lead-206, 82 protons, it's a stable nucleus, and so that's not going to decay. So in this case, uranium-238 undergoes 14 sequential decays until it gets to a stable nucleus, and lead-206 in this case. And a lot of these decay series end in lead with 82 protons, which 82 is one of those magic numbers. Okay.